Have you ever really thought about what's going on inside a hot air balloon, or even just your car tires? It all comes down to how gases behave, and today, we're going to unpack the combined gas law. Think of it as the ultimate multi-tool for understanding gases.
So let's start with a real-world scenario. You're on a long road trip, the sun's beating down, the asphalt is hot. All that heat and friction warms up your tires. Now, the amount of air inside isn't changing, but something definitely is. The pressure is building up. The big questions are how and by how much. This is precisely the kind of puzzle the combined gas law helps us solve.
Okay, so before we can wield our awesome multi-tool, we've got to understand the individual pieces it's made from. There are three basic rules that form the foundation, and each one describes a super simple relationship between two properties of a gas.
First up, we've got Boyle's law. This one's all about pressure and volume. And honestly, it's pretty intuitive. You've felt this before. If you take some gas and squeeze it into a smaller space, decrease its volume, the pressure inside is going to go up. It's like pushing down on a bicycle pump. One goes up, the other goes down. Simple as that.
And this graph shows that relationship perfectly. See that nice curve? As the volume along the bottom gets bigger, the pressure on the side drops right down. It's the perfect picture of what we mean by an inverse relationship.
All right, next we have Charles' law. This time, we're looking at volume and temperature. And these two are buddies. They do the same thing. Just think of a hot air balloon. You heat up the air inside, the temperature goes up, and the air expands. Its volume increases. That's what makes the balloon rise. Cool the air down, and it shrinks. They're directly related.
And check this out. No curve this time. It's a perfectly straight line, which just drives home that direct connection. As the temperature along the bottom increases, the volume goes up in perfect lockstep. It's simple, it's direct, it's proportional.
Okay, our final building block is Gay-Lussac's law. And this one takes us right back to our car tire question. It connects pressure and temperature when you can't change the volume. If you heat a gas in a sealed, rigid container, those gas particles start zipping around way faster, slamming into the walls harder and more often. And what does that do? It cranks up the pressure. And yep, you guessed it, the graph tells the same story. Another straight line. As temperature goes up, pressure goes up right along with it. So now we've got our three foundational rules. We are ready to build the multi-tool.
So let's see how we can put these pieces together to build something way more powerful. I mean, why juggle three separate rules when you can have one master equation that does it all?
And here it is in all its glory, the combined gas law. It looks a little intimidating, but it's actually super elegant. It just lets us connect the pressure, volume, and temperature of a gas in its initial state, that's all the ones, to its final state, that's the twos. It's everything we need, all in one neat package.
Now, this is the really cool part. This is why we call it a multi-tool. It's not some brand new law, it's just all the others rolled into one. So let's say temperature doesn't change in your problem. Well, you can just erase it from both sides of the equation. Poof! And what are you left with? P1 V1 equals P2 V2, which is just Boyle's law. It's so efficient.
Okay, so the theory is great, but let's get our hands dirty. This is a practical tool, so let's walk through an actual problem and see exactly how it works. All right, here's our challenge. We've got a gas, and we know its starting volume, temperature, and pressure. Then we change both the temperature and the pressure. The job is to figure out what the new volume is going to be. Now, before you even think about touching a calculator, the very first thing you should do is organize your data. Make a simple table like this one. List all your before values and all your after values. And notice something really, really important here. The temperature is in Kelvin. This is non-negotiable, folks. You have to convert from Celsius to Kelvin because these laws only work with an absolute temperature scale. See? Once everything's laid out in that table, the next step is a piece of cake. We just rearrange our equation a little bit to solve for the thing we don't know, in this case, V2. And then we just plug in the numbers. That simple little table saves you from so many headaches.
So you run the calculation. All the units cancel out nicely. And what do you get? 800.0 milliliters. Now wait a second. Isn't that the exact same volume we started with? How's that possible? Well, think about it. We doubled the pressure, which should have cut the volume in half. But we also doubled the absolute temperature, which should have doubled the volume. The two effects canceled each other out perfectly.
So, let's just lock this in. To wrap up the how-to part, here are the golden rules. Rule 1, always, always, always use Kelvin. I can't say it enough. Rule 2,
Make sure your units match on both sides for pressure and for volume. And rule 3, start with that solution matrix. If you do these things, you will nail these problems every single time.
But, there's a big question looming here. All these laws, this whole multi-tool, it's all based on the idea of a perfect or ideal gas. So the question is, how well does this stuff actually work in the real world with real gases?
I mean, it's a completely fair question, right? In our model, gas molecules are just these tiny little points with no size that don't interact. But real gas molecules, well, they do have a little bit of size, and they do bump into each other. So is our super tool actually useful, or is it just a neat math trick? And this slide really breaks down that difference. An ideal gas is a perfect concept. A mathematician's dream, really. It's clean, it's simple. A real gas, like the air we're breathing right now, is a little bit messier. The particles take up a tiny bit of space and they do interact.
So how much does that real-world messiness actually matter? Well, let's look at a number. For an oxygen molecule, this number right here represents the ratio of the molecule's own volume compared to the average empty space it gets to fly around in. And wow, that is an incredibly tiny number. It means the molecule itself is just a ridiculously small fraction of the space it occupies.
And this right here is the key takeaway. It's the punchline. Because that ratio is so incredibly small under most normal conditions, the difference between an ideal gas and a real gas is practically zero. For almost everything you'll ever need to do, the combined gas law is an amazingly accurate and reliable tool.
And that leaves us with a final thought to chew on. We know this law works beautifully for everyday stuff. But what happens if you push a gas to the absolute extremes? What if you crank the pressure up to something immense? Or you drop the temperature down close to absolute zero? At what point do those tiny, real-world details start to matter? That's when things get really interesting, and that's where the real frontier of gas science begins.